Hi, everyone. My name is Julia Glenday, and I'm part of the project team for a WRC project with a quite long name, Modeling Uncertainty and Reliability for Water Resource Assessment in South Africa, which we abbreviated to MURA. And this is the feedback session for the Catchment Hydrology Model-a-thon that we kicked off last October and wound up the submissions. Around the end of the year, we had some resubmissions in Jan, and then been doing the analyses ever since. Oops, there we go. I just wanted to introduce the project team on this project who've been working on the Model-a-thon and other related activities in the project. We come from a variety of institutions, as you can see, but it's myself, Shaden Gokul, David Gwapedza, Petra Holden, Faith Jumbi, Peniso Meto, Alana Rebello, and Jane Tanner. I'm going to be presenting today, but I hope others will all jump in. Not everybody was able to join today, unfortunately. So I'm going to go through the Model-a-thon submission analyses, what we got from what everyone submitted. And I'm going to try and go through that without pausing unless there are some big clarification questions, like you don't understand something. But please do type questions in the chat as I'm going, and do stop me with your voice if there's something that is very unclear. And then what I'll do is I'll go back at the end and go through all the questions in the chat. Also, other project team members, if you see a question in the chat that really is a clarification question, please jump in and stop me, and otherwise we'll come back to questions at the end. And then we want to discuss quite a few things with you, get your ideas about what the implications of the results really are, and then we'll recap what's happening next with the project. So some of the discussion questions, I'm just going to put them up here now so that you can think about them as I go through the results from the Model-a-thon. Firstly, are there any further analyses that we should do with the Model-a-thon submissions, things that occur to you that would be helpful to look at from what we have? Also, is the level of structural uncertainty that we saw in this activity, is this likely to be representative of other cases as far as you can see? And what are the practical implications of this level of uncertainty and prediction that we're going to look at? And what are some feasible approaches for assessing prediction uncertainty in more applied settings? What can we do to reduce that uncertainty? And then kind of recap what are some key take-home messages from this activity that we should make sure to communicate when we write it up to your mind. So, quick recap, the Model-a-thon was many different people modeling the same catchment using the same data sets. And then taking that model and using it to look at a change scenario, in this case, a land cover change scenario, to predict the impact of that change on stream flow and the overall water balance. The point of doing this was to explore how differently do different people put together models of the same thing, using the same modeling tool or using different ones. And how much do those differences matter to performance and to the overall change prediction at the end of the day? This is, if to put this in more theoretical terms, this is looking at structural uncertainty, but there's many different types of uncertainty in modeling, such as uncertainty in the input data and the calibration data, and uncertainty in the parameters we use. And then structural uncertainty is the leftover that you would still have even if your input data was perfect, your calibration data was perfect, you knew what all the properties of the catchment were. You would still get different outputs from different models because they simplify the world in different ways. Even if your data was perfect, you could get these differences, and that would be the structural uncertainty in your predictions. And which structure is giving you a more realistic output. And if you're not able to discern that, then the range across some different structures would be your structural uncertainty. So in this example, the input data wasn't perfect, none of the data was perfect, but everyone used the same data. So what we're getting at is more of that structural uncertainty, and as well as some parameter uncertainty in terms of how people took the data and went through to parameterize their models. So these types of uncertainty have been studied, and their relative contributions have been studied in a few different studies, but these tend to be on quite lumped models. And in South Africa, in applied cases, we use more distributed models with different land cover types and within them for decision making. And this really hasn't been looked at in that kind of a context very systematically. So that's what we wanted to do here. And some of these previous studies on the simple models have shown that the structural uncertainty can be the largest portion of prediction uncertainty in some of the studied cases. So we gave all the Model-a-thon participants, the 2 streams case study. It was selected for its particular land cover and land cover history, as well as the data availability for it. But that was a trade-off in that the catchment is quite small, smaller than some of the models are often used for, although there have been cases using all the modeling tools of very small catchments that we've seen in consulting reports and literature. The scenario that people were asked to model was to convert the wattle plantation, which covered 60% of the catchment area, into sugarcane. And everybody was given data for a calibration period when the wattle plantation was relatively mature. And that was from 2000, like water years 2010 to 2014, or I'm giving dates because people list water years in different ways sometimes. And then asked everyone to look at the scenario of that cover change for actually a longer period that included some wetter times. So there is the limitation as well that the calibration period was drier than the change assessment period. But that's also a typical use case, reality case, even with moving models forward into climate change at scenario modeling, etc. So who participated in the Model-a-thon? I'm not naming names, obviously, but what was the sort of spread of experience and different model tool users, etc. So we had 40 individuals who signed up, and we had 14 individuals who submitted models. So 35% of the people who signed up made it through to completion. So thank you everyone and thank you also to people who tried and didn't make it through, because I know it was, we appreciate even trying. And then some people submitted more than one model using different tools. And so we had 18 model submissions in total. We had a spread of experience levels attached to those submissions, most of which were intermediate experience level, as you can see there in the pie chart in the green. Most people who submitted, or most of the submissions, were from people in academia and research, and that included postgrad students, which made up about a third of the submissions. And I should acknowledge that 44%, or 8 of the submissions, were from the project team. We didn't communicate with one another when we were doing our modeling, so it was still independent, but it is true that people in the project team had had a longer time to think about the catchment beforehand. But that may or may not impact things. The tools that were used, we had submissions from the 5 main tool types that commonly are used in South Africa according to a previous survey that we did. So we were happy to see that, and we had multiple submissions with most under all the tool types. There are a few different versions, so like ACRU 3 and ACRU 4 and ArcSWAT and SWAT Plus, and you can see the distributions there. But for the most part, there were multiple submissions in any given tool, so that was helpful. 61% of the submissions were using the South African models, so the different WRSM Pitman, SPATSM Pitman, and ACRU versions. So we were happy to see that spread of different models in the submissions. The majority of people spent 1 day or less on the activity. We were wondering how long it took people to do it. We were trying to make it so it could be done in a day. But the maximum time spent was 4 days, and I'll come back to the the implications of that later. In terms of calibration, 3 submissions used supervised automated calibration. 11 submissions used manual calibration, and 4 submissions didn't attempt any calibration. They just put in what they thought would be the best parameters, ran it, and submitted. And we did have a survey where we asked people to comment on their submissions, etc. And those ones tended to actually be expert users who didn't have any time because they are very busy people. And so we're grateful that they submitted models, but they that's why it's not what they might normally do. But it was, yeah, quick setup, quick submit. We had quite a few monthly models. A third were the SPATSIM, WRSM and SPATSIM monthly models, but other models also submitted in a monthly time step, because you can do that in SWAT, even though it's actually calculating at a daily time step, if I understand correctly, and then it's amalgamating the outputs. Then in terms of spatial units, we had models of very different structures. The most frequent was to have 3 units, be them HRUs or otherwise, depending on the tool, how they call it. And that was in line with the land cover. Some people used more, some people used less based on the tool. Just as a reference, amongst the SWAT users, the number of HRUs in the submission ranged from 14 to 4,316. And then in Mike Shee, both submissions used a 10-meter grid, which resulted in 7,382 cells. So you can see we had from quite lumped to quite discretized models. And so here are the results. The black line, this is monthly stream flow put into a measure of runoff in millimeters per month as a time series. The thick black line is the observed data. So you can see the spread of the different submissions. And we then applied some criteria for acceptability based on literature, accepting models that had NSE and NSE of log transformed flow, the monthly time step of over 0.5, p-bias of less than 25% or less. Sorry, I should have had the equal sign there. Same with the log, it's greater than or equal to, sorry, the NSE p-bias is less than or equal to 25%, correlation of greater than or equal to 0.6, and Klein-Gupta efficiency of greater than or equal to 0.5. So these are things that can be debated if you have input on them. We loosened them a little bit. We started from the literature values, and like for some of the NSEs, it's 0.6 generally suggested. We loosened it to 0.5. And when we did that, we got the following results. So the model numbers, this is sorted by those that met several criteria and then sorted by NSE. So if we selected models that met at least 4 of the criteria, we had 6 of them, and we thought those could potentially be accepted for looking to apply further to look at the scenario change. And you can see the ones there. Some of the highlighting is incorrect. I need to fix that. But what you can see is that there were accepted models from a range of tools, 2 from SPATSIM, 2 from WRSM, 1 from ACRU, 1 for using Mike Shee. You can also see that the Pittman models dominated the set. In terms of calibration approaches, the 2 highest NSE submissions used supervised auto-calibration, but those weren't the best for all statistics. And those were also the ones that used the most time to prepare the models. The models without any calibration performed very poorly, often having negative NSE. They're not shown there, but over and above that, in general, the more time spent seemed to result in higher performance across the intermediate and experienced levels, which was interesting to see. But given that this was such a short, well, you see good spread actually at about 1 day, but it was interesting to see that increase. But given that it was such a small case study, it's just interesting that it could take much longer than that to get a good performance. And what does that mean for other projects in terms of time needed. So then these are the results for the accepted models. So you can see much tighter fit in terms of monthly time hydrograph, but you do see there is some spread. There's some events that are captured in some and not captured in others, even though the rainfall is the same. So there's some thresholds that are different across the models for creating a flow response, and you see a difference in base flow, etc. Looking at the daily models, so this was for a month, so those were accepted based on their monthly performance. And some of the models we looked at all the models monthly. We aggregated daily data to monthly so we could look at all of them together. And then we also looked at the daily ones separately. And only 2 of the models of the daily time step were selected in the monthly stats assessment. We also tried to apply a daily stats assessment. We had to relax the criteria quite a bit. And the only 2 that met all those criteria that you see there were the same ones that were selected using the monthly criteria. So you can see there are some issues with getting the recessions and some of the peaks. Some of that might be due to the observational data. So the models couldn't have gotten it anyway. So here's something interesting. I'm going to unpack this figure a bit because it's difficult to look at for the first time once you get the hang of it. So these bars are different water balance fluxes, and it's the range of different water balance fluxes across the set of accepted models. So if you look at the x-axis, there's different fluxes, and the ones with the star are contributing fluxes to the bigger capitalized one. So ET total is made up of interception, evaporation, and ET from soil, ET from groundwater, which not all of the models do. And then, for example, runoff total is surface runoff, interflow, and groundwater contributions to runoff. And then the colored blocks represent the range of mean annual fluxes across the set of accepted models. So what you see is that there's relative agreement across the models in terms of the very basic water balance. So the size of the block for ET is quite small. It's not such a big range for total catchment ET, and same for runoff total, which we would expect because they were predicting, they calibrated reasonably well against the observed runoff. So they should all have quite similar runoff and hence quite similar ET given the rainfall. But what's interesting is that the models that were accepted vary quite a bit in some of those contributing processes. So for example, if you look at the contributing runoff fluxes, surface flow contributions ranged from 0 to 65% of the total runoff. You can see quite a wide surface runoff bar, and same for groundwater runoff bar. The different models had either 5%, had a minimum of 5% of the runoff coming from groundwater to up to 83% of the runoff coming from groundwater. So those are quite different. The models are doing quite different things to get to these similar runoff and similar ET at the end of the day. If we want to look at, are these modeled water balances realistic at all? So this is again for the calibration period. We went to some of the literature on the 2 streams catchments. Unfortunately, things are measured at different time periods and different spatial scales and stuff. So it's quite rough to compare to, but isotope studies suggest that the stream flow is generally dominated by subsurface flow, potentially deeper groundwater. There was overlap in the signatures, but generally that was the conclusion from those studies. And most of the models did have subsurface flow, either interflow or groundwater outflow as dominant, except for one, which was P43. That was a WRSM model, but then PO1, which is also a WRSM model, did not have that. So it's not that it was about WRSM, it was about that setup. And then declining soil moisture and groundwater levels were observed over this period. And you see that in all of the models except for one, which is P21, there was a small increase in storage, net increase in storage over this time period. Sugarcane ET measured in the field using scintillometry was around 630 millimeters per year. The models were pretty good at getting quite close to that for the sugarcane. Then the wattle, a mix of scintillometry and a few other methods, estimated at about 1,130 millimeters a year for this same time period, and the models were far less than that. So I'll come back to that in a sec. And I welcome people's input on what to do with that information. Then the wattle canopy interception was measured for a slightly different time period than this, and it was estimated that it would be 20 to 24% of the rain. The models covered that, but one or two were much lower than that, and some were a bit higher. Again, that was measured for a slightly different time period, though. So we have some indications of realism. There's some things where you might want to go back and revisit some of the models, despite them giving acceptable streamflow. We decided to proceed with all the models based on their streamflow performance, but this is just a flag. This could be a way to potentially, even reduce from the 6. And then there is a time series data of estimated wattle evapotranspiration from scintillometry and from an eddy flux tower over this time period from late 2009 to 2013, which is that black line. And then these lines are ET from wattle estimated by the different modeling tool, different models submitted. And you can see there's not a very good fit there. And the models generally have way too low ET in the winter part of the year, the drier winter part of the year. So that could indicate that the models are not allowing the vegetation the access to deeper water sources, for example. But none of them seem to do it particularly well. Although if the ET was much higher in the model, the runoff would have been much lower unless there were other storage changes. So that would be another. So the field studies for this catchment, they thought that this high ET was being fed by a net drop in storage over time. So what this graph shows now is if we take these models and we apply them to the scenario, so that's increasing, that's looking at the streamflow increase when we replace wattle with sugarcane. So this is scenario minus baseline. You see a range of patterns and magnitudes of change prediction here. So that P26 stands out quite a bit as having a greater increase across the low flows, for example, whereas the green one, P27, that has higher spikes in the high flows, for example. So there's different patterns being predicted. And this is also shown, this is the same graph, but instead of absolute change, this is percent change. So you can see the percent change in base flow more easily. And it's quite different across the tools. So like P43 has much lower percent change in base flow than the others, and even some decreases, actually quite a few decreases in base flow at certain times. And some of the percent changes in peaks can be up to 800%. This is peak monthly flow. So that's quite extreme as well. So if we look at the range in predicted mean annual runoff increase with the scenario across these accepted models, we get quite a big range from 18 to 78 millimeters per year, and that's 17 to 101% of what the baseline values were for those models. In terms of change in the max monthly flow, it ranged from 7 to 100%, and then the change in the min monthly flow, one model predicted a decrease in the minimum flows, and then up to 200% increase in the minimum flows. So that's what we were seeing in those graphs, just maybe summarized more easily. So this bar chart shows the baseline model and the scenario model mean annual runoff, and then the stripy bar is the change. So you can kind of see the spread of changes, and I've organized them into models of different tools. So you can see the 2WRSM, 2SPATSIM, the MIC, and the ACRU. So you can see the ACRU is the one that predicted quite a bit lower change. The MIC model predicted the greatest change out of the set, and then the others were in between. This graph looks at how the water balances changed between the baseline and the scenario. And what the two bars are the minimum and maximum amount of change across the set of models. So you can see there's a range of decreases in overall catchment ET, and the processes that contribute to that, and then again an increase in runoff, and what contributing fluxes increase as part of that. So quite notably, both SPATSIM models actually predicted a big decrease in canopy interception, and that actually led to an increase in ET from the soil because more water was now making it through to the soil than when the wattles were there. The result of that was still a net increase in ET, but it was interesting to see that trade-off with a high canopy interception, the role of canopy interception there, and then feedback. The PO1 WRSM model predicted a decrease in surface runoff, unlike the other ones, but then a large increase in interflow. So there's more infiltration and interflow in the scenario with no wattles in that model. But that didn't happen in the other WRSM models, so they worked quite differently. And then the one MIC model, there was a large increase in groundwater contribution to the stream, much larger change than in the other models. So you can see both their prediction of the change differed, and you can see like the processes contributing to that across the different models were quite different across the suite. To come back to the cases where we had two acceptable models built with the same tool, this is just highlighting these two WRSM models, and they predict quite different amounts of change. So that's just the mean annual runoff range and changes predicted across the two. And just to note, like the PO1 WRSM model had a lot less surface flow, whereas the P43 model had a lot more surface flow and less subsurface flow. So you might expect that they would predict then the impact of the changes to be in land cover to be quite different. Then the two SPATSIM models were much more similar to each other in their predictions, and they also had more similar water balance fluxes. P27 had a bit more surface flow than P21, but compared to the two WRSM models, these two SPATSIM models were quite similar to one another. One was manually calibrated, and the other one was calibrated with an automated tool within SPATSIM by two different people. So yeah, so that's the summary of the outputs, and I'm going to now reveal, I moved to the next slide too quickly, but I'm going to reveal the names of the people who produced the models that met the acceptability criteria, thereby winning. They're Benny Hasbrook, David Guapedza, myself, and Senatemba Totlo. I'm sorry if I've mispronounced. Just listed in alphabetical order. They all, you couldn't really rank the different models because each one performed better on some category than the other ones. And the best student model is by Senatemba, and runner-up best student model is by Penny. I've starred the people on the project team. As I mentioned, we might have had a slight advantage in terms of familiarity with the catchment, but other than that, probably not. People were too busy to spend more time than the time spent by the project team wasn't more or less in some cases than other participants. So well done, everybody, and thanks again to everybody who submitted models. I think it was a good experiment. And now I want to just pause for a bit. I went through quite a lot quite quickly, and I wanted to see if there's any questions that you have or any input you have on the analyses we've done so far and presented. Are there other things you'd like to see, questions you have? I'm just going to open the floor.
Thanks, Julia. That was a brilliant presentation. Thank you so much. Just to say, there's nothing in the chat so far, so it's obviously all nice and clear.
Great. I'm just gonna give a sec. Is anybody?
Right, Mark's got his hand up.
Ah, great. Please go ahead, Mark.
Hi, I was just going to make a comment that what it goes to show, if you, I mean, for example, I submitted a completely uncalibrated, straight off the bat using the data provided, okay? And there may have been other people that did the same thing for a very good reason. And it just goes to show that a good model with, let me just call it, unverified data in dodgy hands is of no use to anyone at all. Because, I mean, I didn't do any adjustments to Acru at all. I literally just took the data, set it up, and ran it and produced those results. So it just goes to show that, you know, we put models out there on the web, we put models out there, we run training courses, but in the hands of the uninitiated, they're actually of very little use at all. Because if you don't know how to modify it, or let's not use the word calibrate, let's use the word tweak, fudge, fiddle, or whatever you want to. If you don't really know what you're doing, a bolt standard model off the shelf with data that's maybe at the wrong scale or the catchment's at the wrong size, just goes to show that if a model isn't used properly by someone who understands how the model works, you actually are really achieving nothing. And so we just need to kind of be aware of that.
Thanks, Mark. Yes, and there was, yes, you had mentioned that actually in your submission survey that you just used the default parameters and went ahead, and then in part because of time. And there was another case actually with Spatim, another person who submitted mentioned that they started with a database of values for the quaternary catchments, and this catchment is tiny compared to a quaternary, but they use the quaternary parameters as a starting point, and then I think because they were trying to hold quite similar or quite close to those parameters when they were tweaking, their calibration didn't turn out very well compared to other models or even other Spatim submissions.
Yeah, I kind of left mine the way that it was specifically. I mean, I could have spent hours, and obviously I know Acru relatively well, so I could have done lots with it. But I left it completely untweaked and untwiddled, just as a comparison point. So you know, you can see that if you don't, you know, with all the best data in the world, if it's at the wrong scale, or you know, you're making assumptions and you're not aware of the assumptions, and you haven't, I mean, there's a lot of stuff going on in TwoStream that if you've been there, I would have put very different data sets in various areas, because if you know what the place looks like. So as Roland would say, go out there and get your hands dirty, and then you might actually do better when you do modeling.
Yes. Thanks, Mark. Does anybody else have anything? I'm going to go on to some of the more targeted
Julia, there's another question.
Oh, great.
Jason's got his hand raised.
Thanks. Right. Somehow I'm not able to, with the share screen, it's hard for me to see the hands. So please just jump in.
Okay, cool. Yeah, hi everybody, and congratulations to all of those who actually submitted models. I'm quite impressed, and the people who submitted too, I think, is absolutely brilliant. Well done. Yeah, just a couple of comments from my perspective, I wanted to participate, but I actually wasn't able to get a model in. I just didn't have the time available to dedicate to that. But I think that this comes to sort of a question on terms of your timeframes for the modeling. Now, I know you gave it several months, but it might be better to have an extended period to see if you can get more sort of submissions in. I don't know whether there's an opportunity to further increase this to get more feedback, but I suspect you're under a timeline yourselves. But yeah, I mean, it would have been nice if we could have got more sort of feedback related to this. But yeah, I mean, I think there's also another aspect that might be quite interesting to review in these setups is you've had calibrated models, or these people attempting to calibrate. Obviously, that takes a bit of time. But it might be quite interesting to run a blind test as well, like Mark did, with all of the different models, just to see if you don't have calibration data, for instance, how well you would score making certain assumptions and setting these models up. Because in certain places, in many areas, we don't have calibration data, and we make certain assumptions related to the models that we're looking at. And then I think so I mean, my question would be is would that not be something that's useful and should be studied and had a look at a sort of later stage? And then I think the other sort of observation that I'd make is that the people who were observing or had observed the catchment and spent more sort of time on these calibrations and stuff obviously generated much better results. But I think that's also due to the fact that they probably also saw the catchment. And I think maybe in a sort of exercise like this in the future is perhaps choosing a set of dedicated modelers who can actually go and view the catchment and have a look at something might be quite interesting. So you have a group of professional modelers that go and have a look at it and have got time dedicated towards that. But I'd certainly look at trying to increase your level of participation here, and it's either extending the time period or making some other method to do that. But I am very impressed that so many people managed to get their submissions in. So just some comments from my side, but well done, everybody.
Thanks, Jason. I'm just going to actually, while people talk, I'm going to add some notes to the slides so that they're captured there. I'm also taking notes in a notebook, but I realize it's better if I do it where people can see them. So I think I got add model setups that use default parameter sets. We did think about, yeah, in this case study, it would be reasonable to do that. It's in some ways there's still how you break up the space that different people will do differently, even if there's default setups or default parameter sets. But in this one, it's easier to do that.
Yeah, and I just wanted to respond to Jason just to say that so the project team has actually been together on 2 projects. The first one was the modeling intercomparison study, and then this is the follow on from that. And we've now spent many years talking about this activity, and I think it's just important to note that there's many ways you could have approached this, many different ways you could have set this exercise up, many different types of uncertainty you could isolate. And this is just what we eventually decided on. But it's not the only way, certainly. But, you know, given budget constraints, given people's time constraints, this is what we could come up with. So certainly it would be very interesting to see more exercises like this in the future, targeting maybe different aspects. And especially if there's money to compensate people's time, you could do more. I see Petra's hand is raised.
Hi everyone, and so yeah, I'm also part of the project team, but I kind of wanted to pose a question to the group to understand like how they feel about the fact that different models set up by different people can achieve comparable accuracy in terms of the stats and thus be used to understand impact of, scenarios and things like that, but predict quite different changes. And what people in the group, like, what do people think about this, and what could the implications be? Because we all know that there are many groups and many studies that are being used that are using one model to understand impacts. So what does this mean? And I just wanted to kind of see if anyone had any reflections on that, or questions, or more questions on it.
Thanks, Petra. Yeah, I mean, essentially what we showed, like, if that set of 6 models that met our acceptability criteria, if those kinds of criteria are the kinds of criteria one might use in a practical setting or not, we could discuss that. If they were, then our uncertainty range on change prediction is quite huge. And the models are also predicting different changes within the water balance, as well as, changes that are driving the different changes in stream flow. For me, it's kind of scary to see that. I don't know, what do other people think when you see that? Like from 17 to 101%.
Yeah, so I think, the key question I think here is are you getting the right answers for the right reasons? And that really is the crux or the main concern that I would see popping through on all of these modeling applications, that you can get such variance between the same model that have huge variance in terms of the outputs and how they've achieved that particular answer that they got. So that's obviously a major concern, and I don't know how you would address it, but it is a key question. So are we getting the right answer for the right reasons?
Benny has his hand up. You want to go ahead, Benny?
Hi, Benny.
Hi all. Thank you very much. Yes, this is very interesting. I'm finding it very interesting, and I do feel that this is a great actually training exercise, where we can see how different people do different things for different reasons. I think it's maybe important that somehow we need to capture, at least amongst the different types of models, the different approaches that was taken and resulting the results that we got from the model. How I approached the Pitman model setup compared to other people might be completely different, but even if it's maybe not right in this instance, we might learn from that, and that's the important thing, that we all can see that there's different ways, because in the Pitman model itself, and I didn't have time to do that, there's 2 or 3 ways that you can actually model this problem. I chose just one of them due to the constraint of time, and I think you mentioned that earlier as well. There's different ways of doing these things, but I think a combined, after the fact, just discussion or something like that amongst the people who did a specific model might be also useful. And then the second thing is, and that's something that I've always been taught, is that it's definitely a case for horses for courses. These models were not all designed to do everything the same and to the same amount of level of detail. So obviously, when people develop a model from the start, it's to solve a specific problem. So, for instance, the Pitman model was more developed for a large scale type of application, and I think they typically also say in the model that we shouldn't go below certain kilometers, which we actually did now, square kilometers, but it evolved over time. And the same with all the other models. They are developed for a specific application, and therefore an exercise like this is actually also very interesting to see, you know, how do we how these different models react to different types of problems, and the thing is, I think we should, if this gets done again, which I hope, there's a wide range of other things that we can also test, and I think you also asked for feedback on that and some of these things, and I really think it's a good thing to do this, but as I say, let's do that extra step afterwards to get together the people that use the same models and discuss what we did, what sources of information you used, and so forth. I, for instance, used some more regional information about or that specific catchment, and added that knowledge to the calibration as well. But well done. I think it's a very worthwhile exercise, and I really support that we do this again.
Thanks, Benny. Yeah, a few people did comment that in the submission survey that they would be interested in doing it again and have other kinds of case studies. I think this one we tried to make this one as simple as possible because of people's time. And so it is tricky because we'd love to do all sorts of case studies if we got funding for another project, for example. It's tricky in finding one that has the data that we can share, for one thing. So as data you can't share at a daily time step without trouble, but I mean, it could, yeah, we could look into that, but things like that. And then also, you know, we struggled to get, we got a good amount of submissions. I was happy with, I think we were happy with 18. We weren't, that was kind of what we were thinking we might get. But I feel like if it's something that's going to take quite a bit longer to set up, I'm not sure how many people will volunteer, but we can say, but now that people have, we've got a few people that are interested, so maybe people would, or get more support for it, so it's less volunteering. I'm not sure. If we were doing a more complicated case with dams or more cover changes or things.
Well, the thing is, I mean, this is capacity building, if I can just carry on to that. So if you can get for funding for capacity building, I mean, I'm sure you can contribute some time towards the people's cost towards the people, payment towards the people's time to do some of it. But as you say, yes, it is for the more detailed models a problem to get that level of detail on a wider scale. But I mean, once again, that's the problem in reality, isn't it? I mean, isn't that then just the test, that you can extrapolate whatever more detailed you need to have for a larger area?
Yeah. Julia, sorry, my hand's also raised, if I may. So I'm also a part of the project team. But just to say that I heard one or two comments come through, and just to address them, I wasn't part of the team that picked this particular case site, but there were like several options, and the team spent a lot of time making the decision. And based on all of the options and the factors, just the realities, they made the best choice that they could. I think the key thing is that already this case study, we've got enough information that makes it's already representative enough of some of the issues we see in modeling any catchments or whatever size. And I also remember Julia saying that, for example, even though Pittman perhaps wasn't designed to work at a very small scale, some of the experts have been known to say that they can even model at the scale of a sort of football field. So I think that it's still valid. And I think there's two interesting...
And it's Alan that always says that.
So I think that there's two interesting discussions emerging, and one in the chat, and I'm just watching time. So I wanted to just, I guess just the one thing, because Julia and Petra had asked, you know, what do we think about this and what should we do? One option is just that, you know, if we take this to be a very realistic case where a consultant got given this particular case study, they had finite budget and time, and they had to come up with a model. If depending on which one they picked and how they set it up and the time they had, they could get vastly different results, and this is of concern. And so the question is what can we do about that? And maybe one option, just to throw it out there, people in the room might have better ideas, would be that we require 2 different models set up to get a handle on that structural uncertainty. And that obviously would require extra budget on consulting projects, but it's something that maybe we need to very seriously start considering in water resource management in South Africa. And then I'm just throwing that out there, it can be discussed, but then the discussion in the chat then is coming around to the fact that the catchment is quite small and quite a tricky one, and that there were some issues as well, or doubts around the reliability of that observed stream flow. And I don't think that this is unique to this catchment. I think often this is the realities of our catchment monitoring in South Africa, that, you know, and discussions around, should we even be using stream flow? Is it reliable enough for calibrating our models? And even when we do we have good enough monitoring? And this is where the discussion in the chat's going now. So maybe, Julia, I don't know if you'd like to pick up some of those comments in the chat, or if you want to refocus around one of your discussion questions, but just to highlight those comments in the chat.
Yeah, no, I'm seeing the things about scale, and we were aware of that, and that in some case, like with applying the Pitman, we just asked people to scale it up by 100, and then we scaled it back down again, which may or may not, but we did try it both ways, and it seemed to not sort of at the millimeter water balance level, they turned out similar when you do that. So, but yeah, I see questions about sharing the presentation. Yes, we'll share that. We will share it afterwards, as well as the recording. And then Alana, you brought it up, and I see also a comment from Jason about models getting the right answers for the right reasons. And I think that's also what you were saying, Alana, with, I think a problem like we saw in this case, it doesn't seem to be enough to only measure stream flow performance, or at least the stream flow performance metrics that we're using are not enough. If we'd been stricter, you know, if we'd added more, I guess, base flow matching calibration criteria or performance criteria to say what do we accepted, etc. You know, we might have got a tighter set of predictions at the end. And then if we want to go beyond stream flow, you know, can we calibrate against, or can we compare our model's performance and realism against some other data? And do we have this other data that we can, what other data could we reasonably use? And so these, what I'm saying, it sort of speaks to this question 4 we have here of like, what are approaches for reducing some of this uncertainty? You know, if the criteria we use to pick, you know, all these models, these 6 models were the ones that met that acceptability criteria, you could go back and revise those. But if we assume those were okay, you know, this level of uncertainty to me is not okay. So then, you know, what do we find, if I go back to what we used, we had an NSE, actually most of the NSEs were over 0.6. There were some over 0.5, but you know, these are statistics that people fairly commonly accept in reports I've seen and move forward with a model that meets these. But it just shows that, yeah, if this is what you use, you can still end up with quite a range. And then if you only come to one model, you won't know. If you pick one model, it could give you some value in between, you know, 18 and 78 millimeters, or you know, 17 and 100% increase. And you wouldn't know without trying any other models that it could potentially be way higher or lower, or so I was just wondering if people have ideas about that. Is it something that you've thought about before? Is it something that you've tackled in projects of your own?
Julia,
I see people
Jason's
raised.
hand is up again. Jason first.
Yeah, please go ahead.
Yeah. So just a couple of sort of comments from my side is a lot of the stuff that I'm not being critical of the approach that you've used. I think you've done a brilliant job here in terms of getting people to do the feedback. I think that you've got an excellent number of people running that, and given the sort of budget and time constraints, I think you've done brilliantly. So the comments that I put in there are more to discuss sort of further research that you might apply for. But I mean, certainly from my perspective, I think that this is an extremely valuable exercise, and I think it should be built on into further Water Research Commission research that could potentially have a look at a different area, longer time periods for the modelers to get hold of things and to run these type of structures and stuff like that. So I think you have done brilliantly. Yeah, I think just the one comment is that yes, it would be nice to have a catchment where there's perhaps more information on certain elements that are changing in your water balance structure, like in the groundwater and in the maybe you've got measured evapotranspiration and these types of things where you can actually see the differences a bit more effectively. But I certainly think that you have done a fantastic job. And yeah, from my side of things, I mean, if you go for additional funding to further this type of study, I certainly support that, and be happy to sort of help with those motivations if you need them.
Thanks, Jason. I see we're coming to the end of our time. People have brought up some really good points in terms of looking at how we evaluate, like Benny, you made some great points about capturing the process of what decisions were made and setting up the model and discussing those and capturing those and trying to learn from those in groups, which I think is really important. And then also, I think Jason and a few others have also mentioned finding other, and Alana as well, finding other ways of looking at how realistic our models are. Just to note on that, this catchment actually does have measured evapotranspiration in the field, and none of the models got it very well. But this data was not given to participants to use in calibration, because the idea was to sort of demo the case where you only have streamflow, which is generally what people use. So it would be interesting, I think, to see what people would do if they're then given this ET data and said, can we try and fit that as well?
Chair, can I just quickly?
Yes, please.
Oh, sorry. Yeah, just I want to support exactly what Jason said. All my comments were definitely not critiques about your decision on what you did here. You did a brilliant job. I also would like him support any going further and motivating for any further that, and I will also assist with that if necessary. I just want to add to that the amount of people or hydrologists that can actually help with this country's water resources challenges in the future is becoming less and less. I know every year more and more people get trained and so forth, but if we look at the work that we typically do for water affairs and the large projects that they are calling for in doing large-scale hydrological analyses and so forth, the number of people that have got experience with doing that is becoming less and less. We're losing them at a big rate to overseas countries, of which the least is definitely not the UK. And yeah, I think training people with actual physical model, running models, coming up with answers and talking about it afterwards would be of great help to not only this community, but also to the country in large. And then I want to just, somebody mentioned the issue about the flow data. Yes, I agree. Sometimes the flow data is not even worth using it, and obviously different gauging structures. I think this was a V notch or something, has got a certain amount of uncertainty around that, and I think in future we need to take that into account as well. So and obviously also, as Jason I think mentioned, we need to look at some of guidance on groundwater parameters. I mean, there are known recharge estimates for the area, which I also used to get my recharge, you know, alongside regional estimates for that. So maybe just adding something in that base flow. I mean, you don't measure base flow, unfortunately. You can deduce some of it in drier periods, but it's just an indicator of what's going on. But at least some of the groundwater parameters in the area can be used as a guide of what's going on in the stream. Thanks a lot.
Thanks, Benny. I've noted those. That was really helpful. And yeah, thanks everyone. I'm going to, unless somebody has, I've taken a lot of notes from this, and we've also got notes in the chat, and this is being recorded. And the team are also noting what has been said. And Benny, I appreciate that. Like, yeah, the need for more. It takes a long time to get one's head around these models beyond just getting the software to run without an error. You know, yeah, to have more groups that sit and talk through why we set up things the way in different ways. And so that point is well taken, and looking at what other data sets, you know, can we be accessing to improve realism here. So thanks everyone. Unless anybody has any final burning comments, I think I'm going to close the session.
Julia, maybe just a note on the way forward.
Yes, yeah, that's what I was.
Cool.
So I have this quick slide. So what are some of the next steps in this project and with this activity? And yeah, essentially, well, recognition for the people that I mentioned who essentially we're the winners of the Model-a-thon, and Sunitamba, you'll be receiving a prize as well, because students we were trying to incentivize students to participate as well. And we're going to turn this into a paper, and we'll be in touch with people who submitted models if they want to engage further on drafting it as well. And another big step in this project too is we're going to work on a policy brief around modeling uncertainty, and I think a lot of the comments made here today are informing that. But the idea being that it's you know, it's sort of targeted as people commissioning modeling studies to be aware, you know, of some of the effort and time needed to reduce this uncertainty. And I think, because I think not everybody is aware of that or gives time for it. But yeah, to flesh that out a bit and get people's input. So please be on the lookout for communications around that, and then all of this is going to get wrapped up into WRC project report as well, but with hopefully shorter, more readable product outputs, the paper and the policy brief. Yeah, I see a few more things in the chat. We'll capture those. And yeah, thank you. Thanks everyone for coming. And thanks everyone who participated in the Model-a-thon, tried, and those who finished. And yeah, it was a really, we were really happy to get as many submissions as we got, and we really appreciate everyone's time, and I hope you can see the fruits of it.
Thank you, everybody. Thank you, Julia.